Welcome. This is a talk about quantum computing, which should be pretty easy, I reckon. How hard could it be? Just to make sure that you're all still awake before I do proper introductions. There we go. Right, so I'm going to have a thought experiment, which you might have come across before. Just imagine for a second, this is what Schrodinger's cat is about. You take and you put a cat into a box, and inside the box you have a radioactive isotope that will decay at some point in the future. We don't know when. Inside the box, you also have some sort of mechanism that if the detector detects that the isotope has decayed, then it smashes the vial of poison and the cat dies. Now bear in mind, you can't see this. This is happening inside the box. The question is the cat alive or dead? Okay, so the answer is it's alive and dead until it's observed. Right, I think we've set the scene now. Right, so this is a little bit about me. My name is Brian Douglas. I'm a software engineer. I worked as a physics teacher briefly when the dot-com bubble burst. I taught physics up till A-level. I started Code and Fury, my company, in 2012, delivering IT training and delivering software projects. And today, Code and Fury specializes in training for data science. But probably the bit we're most interested in is the physics teacher bit, because I thought I had a fairly good grasp on physics before I started this. And what I actually discovered was my physics is pretty good up to about 1920. So that's about 100 years, okay? And for that reason, I'm not taking questions at the end. There's 100 years of physics there. I'm not going to take questions. But I will hang around at the end if people have got individual questions that can come and talk to me. So, one of the things that I find one of the biggest challenges in preparing for this was that, in general, I find that people explaining quantum physics tend to oversimplify, and I'm going to try not to do that. And those oversimplifications tend to lead to a lot of common misconceptions being perpetuated. So this is a quick overview of my course, or my talk, in no particular order. We're going to do a crash course in quantum physics. We'll address some of those misconceptions. We'll ask, what is quantum computing? We'll learn some quantum computing principles. We'll get hands-on with quantum computing. We'll find out what quantum supremacy is and what are the quantum computers good for. Why would you use one? What are they for? Finally, we'll find out about the current state of quantum computing. So hold on to your seats. This is the hard bit, the physics. So if we think back to what you learned at GCSE, you probably learned Newton's laws of motion. So that idea of almost a clockwork universe. Everything is predictable in the macroscopic world that we live in. If I flick this bottle off the table, you should be able to use the laws of motion to predict what will happen next. Now, if you take that to the extreme, then everything should be predictable in this universe. It's the idea of determinism, of saying that you can predict, if you knew all the factors, all the variables, you'd be able to say what happens next, even to the extent that I should be able to predict whether you're going to have coffee or tea at the next break. Now, I don't think the world really works like that. And I think that's the whole point in the thought experiment of Schrödinger cat, that you don't really know what's going to happen. There's an unpredictability about this world that we live in. Particle physics, I'm not really going to explain much about. I think you should have a good idea of what a particle is. This idea of billiard balls bouncing off each other. But what I am interested in talking quite a bit about is wave characteristics. So you might remember this from your days at GCSE physics. It's called the ripple tank. So what we have here is we've got a tank of water with a light shining down through it. You put, I used to use like a 50 centimeter rule with a motor on it that would go up and down, and it would create waves across the tank. And then the light shining down through produces a shadow that you can then observe easily what the waves look like. What you learn from these experiments at GCSE is that waves can reflect, they can refract, and they can diffract. The last one is a wee bit more complicated. I think we all kind of know the idea of a refracting waves, your glasses, so light bending. We all know about mirrors, but this one here, this is where you have a gap So diffraction means that if you have a gap and a wave passes through the gap, it will tend to spread out after it has passed through the gap. And if the gap is about the same width as the wavelength of the waves, then you'll actually get this semicircular pattern. So another feature of waves is that they can interfere. So in this case, you can just imagine me standing at a lake and I'm just dropping in pebbles, 2 pebbles at once, and you get the ripple effect. But the waves are actually overlapping and they're interfering. And at this point, I'm going to introduce a new word, which is superposition. So we're saying that the waves are adding up, they're adding on top of each other, they're superimposed. So when we talk about superposition, we're talking about waves overlapping. So if we were to do a ripple tank experiment, we have some waves coming into a gap. You would find you get these semicircular patterns coming out. If you had 2 of them side by side, 2 gaps, then you would actually get the waves interfering with each other. Okay, so this is what it would look like if we did this in the sea and we had some harbour walls set up here with some gaps in them. You've got 2-metre high waves coming in, and this is real water waves being photographed. And just imagine for a second that you're in a boat. Well, if you happen to be here, well then the waves are adding up on top of each other. So you've got an interference pattern, and anywhere in this section, the waves are adding up to 4 metres high. You don't want to be here. But just off to the side slightly, there's these lines. There's one, there's another, there's another, there's another. If your boat is in one of those lines, you've got destructive interference. A crest of one wave is cancelling out with a trough of another wave. And actually, if you just sit here, you're in calm water, nothing's happening. So the question then is light a wave? And if light is a wave, you should be able to pass it through 2 slits. I actually brought my laser gun, and in my pocket I've got 2 slits, and I can try this later if you want to see it, just in case you don't believe this really happens. But it needs a dark room, so it probably wouldn't work too well in here. So what we're doing is we're passing laser light through 2 slits, and what you find is you get this pattern builds up on the wall. You get a bright spot in the middle and different fringes off to the side. And as it turns out, if you were to look at water waves coming through 2 slits, then you would find the same pattern. So here you've got them adding up, and here you've got them cancelling out. And in terms of the light waves, you can see how that lines up. That's where they add up to make bright spots. And over here, this is where they cancel out, and that's why you get the dark spots. So this is the result of an interference pattern. The conclusion, I guess, we can say is that light is a wave because it diffracts and it interferes. Now, a little caveat is they've done this sort of experiment as well on particles. So, they've done this experiment or other experiments on light and shown that sometimes light behaves as a particle. That's what I meant to say. Which brings us to the idea of wave-particle duality. It was Einstein that first put forward the E equals mc squared, which says energy and mass are 2 sides of the same coin, basically. There's an equivalence between energy and mass. De Broglie then put forward this equation in 1924, which says that you can work out the wavelength of matter. So for an electron, you can actually work out its wavelength using this equation. In fact, I could take this to the extreme, and I could work out your wavelength as well. The one that you probably haven't seen before is a Schrödinger equation down here at the bottom, and it was only 2 years later. Erwin Schrödinger published an equation explaining how a matter wave could evolve over time. So this is actually saying if you have an electron incident on something, you can predict what's going to happen next by modeling that electron as if it were a wave. That's an interesting idea. So, is this all mathematical hocus pocus? Let's see if we could do an experiment to find out. So, if we put an electron gun here, this is straight out of your old CRT TV, which was an electron gun. So we put an electron gun here and we fire electrons at 2 slits. The question is, what happens? What pattern builds up on the screen? So we've got a screen here that's covered in some special material. If an electron strikes it, it gives off a photon of light, and therefore we can see where the electron has landed. The question is, what happens when you fire electrons at the two slits? Do they appear like particles or do they appear like waves? So if the electrons are particles, then it'd be like putting sand through two slits, and what you would get is two piles of sand sort of roughly below where the two slits are. If, however, the electrons behave as waves, then you'll get this pattern building up. Which do you think it is? Well, as it turns out, you get the interference pattern on the screen. So that proves that electrons in this experiment are behaving like waves. Now, I don't know what you're like, but certainly if I was at a birthday party and there was a magician and I saw something like this, I'd go, flip me, that's like magic. I would be trying to look up the magician's sleeves. How does that work? What's going on? So let's see if we can't look up nature's sleeve and find out what's going on. So if we fire the electrons through the two slits, then you get the interference pattern. So what I'm interested to know is, what if I send one electron through the two slits? Surely then it has to go through one slit or the other. The interference pattern surely is a result of electrons, plural, going through the two slits and interfering with each other. What if we put one through? And another? And another? And what we find is if we build up the pattern, it's the interference pattern that we've seen before. Weird. Okay, well, the big question then is, could we try and look a little bit harder? What if we put a detector then behind one of these? Because surely the electron's going through one slit or the other. So if I put a detector behind one of the slits, what happens then? It behaves like a particle. So what you get is some electrons are hitting the detector, some electrons are coming down here and hitting the screen, but it's like the two piles of sand. That's a bit weird. Right, well, hold on a minute. Maybe the problem here is our detector. What if we make it a bit less intrusive and we move it off to one side to see what's happening? Well, now something really interesting happens. If the detector's off, then the electron behaves like a wave. If the detector is on, it behaves like a particle. Very strange. People have even done what's called delayed choice experiments, because what we're doing here is we're trying to detect it after it has gone through the two slits. Then we've tried to do if it's on or if it's off. Why would that have an impact? Surely we're already on the other side. Surely the electron has already made up its mind whether to be a wave or a particle. So in one final effort, what we'll do is, we know what speed these electrons are coming out of our gun at. So what we'll do is we'll wait. We'll wait until we know the electron has gone through the two slits, and then we'll turn on the detector. And what we discover, it behaves like a particle. It's mind-blowing. This is why we've got this kind of idea of Schrodinger's cat. The cat is alive and dead until we look. The problem here is that we are looking. And once we look, then it behaves like a particle. Now, as it turns out, you can never be completely uninvasive. When a measurement is carried out, then what happens is it reveals a particle every time. It's kind of mind-melting. If you're confused right now, don't worry. It means you're getting it. So this is going back to Schrodinger's equation. Schrodinger's equation is actually saying that we can model an electron as a wave over time. So when we look at our two slits, surely something is going through the slits. Surely with one electron, something is going through both slits. And we call that the wave function of the electron. So this is a mathematical entity. And we can actually model it, and we can say, yes, the electron goes through both slits, or the wave function of the electron goes through both slits. But as soon as we measure, the wave function collapses, and it reveals a result of where the electron actually is. Okay? So when we look, it behaves like a particle. The question, of course, is it the act of looking that causes the wave function to collapse? I don't think there's many physicists these days that actually believe that a consciousness looking is what's causing this to happen. The rationale that they would give is they would say that as the electron goes through, the wave function interacts with the microscopic world. So if it's interacting with a larger quantum system, then the wave function collapses and gives the result. May or may not make sense. It'll make a bit more sense later when you see this in the context of quantum computing. Now, just to melt your head completely, it's actually possible to send an electron through in a superposition of two states. So we could actually have one electron going through in a superposition of going fast and slow at the same time. Weird. So that's another concept, is that you can put one particle into two states simultaneously. Right, now on to quantum computing, the good stuff. Right, a normal computer uses bits, which are on and off. A quantum computer uses qubits. And a qubit can be on, off, or both at the same time. Now, of course, both is a superposition, and that's only true until we look. So when you get to the end of the experiment that you do your quantum computing calculation, you never find a qubit in the both state. It collapses so that it's either on or off. When you look at qubits, they can hold much more information than normal bits. So for example, here we've got 4 bits. We're trying to hold all the information 0, 0, 0, 1, 1, 0, and 1, 1. So you've got 2 classical bits that can hold these 4 values. You can do all of these with 2 qubits. So with 2 qubits, both and both, you're holding all 4 states at the same time. And you can actually scale that up. So if you have 3 qubits, then you can hold 8 states simultaneously. And in order to do that, you actually need 24 bits to be able to do that. So what we're finding here is that qubits can hold way more information than normal bits can. And this is one of the benefits of quantum computing. It actually turns out if you could get to 300 qubits, then your computer could simultaneously hold 2 to the 300 states. And that's actually more atoms than there are in the visible universe. So just to give you a bit of context, the biggest quantum computer at the minute has 72 qubits, and it's owned by Google. So as we look into quantum computing, we're interested in quantum supremacy. Quantum supremacy, the big question is, when is that going to happen? Quantum supremacy is when a quantum computer can do one task, whatever that might be, faster than a conventional or classical computer. Now, there's lots of misconceptions about quantum computers. This is one that I actually came across as I was researching for this talk. What about solving a maze? A classical computer might approach it like this. You've got a simple algorithm that says, keep turning left, and it finds its way through the maze. So this is one of the misconceptions I hear people saying. A quantum computer would approach this, and it would be able to find all routes through the maze at once. It's instantaneous. It's amazing. It's a little bit too good to be true, though. So while it is true that a quantum computer could hold all the information, all the different possible states in memory at once, what it can't do is, it can't, I'm getting ahead of myself. So it can hold all this information, but what we don't have is the answer. We don't know which one is the route through the maze. What I want you to bear in mind is that the benefits of quantum computers do not come from parallel processing. They rather come from the ability of the qubits to exist in superpositions of states. So while a quantum computer could hold all those possibilities in memory, you still need to devise some sort of algorithm that finds you the right way through the maze. And that could actually take multiple steps to do. Right? So sometimes when you're building an algorithm such as this, you may use qubits in different superpositions, but at the end you make a measurement that causes the wave functions of the qubits to collapse, revealing the result. Right, some different algorithms then. Grover's algorithm is for sorting a database. And let me say if you had a deck of cards with 52 cards on it, and I said, find me the 3 of clubs. On average, it will take you 26 guesses to find it. So sometimes you get it in the first go, sometimes you get it in the last go. Usually it'll be somewhere in between, but on average, it'll be 26 guesses to get the right card from the deck. Using Grover's algorithm, it can say that it can actually be the square root of the number of cards, which would be 7 guesses on average would get you the card that you're looking for. Cryptography is another common place where people say this is where quantum computing will be used. One of the things that cryptography heavily relies upon, things like RSA, rely on the idea of prime factors. Basically, the idea is if I was to say, here's 2 prime numbers, can you multiply them together? You'll say, yep, I can do that pretty easily. But if I was to say, here's a number that is made up of 2 prime factors, it's actually really hard to work out what the 2 prime factors are. And if you get your encryption right, we're talking lifetime of the universe difficult to be able to figure out what the prime factors are. The first quantum algorithm that was actually devised was called Shor's algorithm. And the purpose of it was to demonstrate that a quantum computer, if one could be built, because this was back in 1994, a quantum algorithm that could show that a quantum computer could, in fact, easily work out what the prime factors are. I came across this article last month. There's a paper that was published on the 24th of May, and it says how to factor 204-8-bit RSA integers in 8 hours using 20 million qubits. Now bear in mind, Google's got the lead on this with 72 qubits, so we're a little bit away. So the point in showing you this is just to really emphasize that it's not instantaneous, and no time in the near future are teenagers going to be cracking RSA in their mum's basement. So what are quantum computers good for? Quantum computers are probabilistic in nature, and this means they're good at solving certain types of problems. The sorts of problems they're good at solving are things that are, for example, quantum in nature. So if you're trying to model molecules, then quantum computers are good at that. Something with lots of variables that a normal computer can't hold. Or there's dynamic stochastic problems. Take, for example, you're trying to hold a portfolio of different companies on the stock exchange. And you're trying to work out, will the share price increase or decrease? That's a probabilistic problem. And quickly you can get to the point where there are too many variables for a normal computer to work with. And a quantum computer would be much better at working with those sorts of problems. It would be able to deal with many more variables. So that's a couple of different possible uses for quantum computing. There are different approaches to building quantum computers. Here are 4 that are being done. There's others being done in research in universities, but here's 4 approaches being used by industry. So superconducting, topological, which means qubits in different positions at the same time. Spin state of electrons, which can be up, down, or both simultaneously, or you can have light polarization. Google is the winner at the minute with 72 superconducting qubits. IBM are next with about 50. Microsoft are using topological qubits, and Intel are using the spin state. So let's see if we can have a bit of a look at what this looks like. My recommendation, if you want to get yourself hands-on with quantum computing, my recommendation is to start here with Microsoft's Quantum Development Kit. You write your code in Q#. You use Visual Studio or Visual Studio Code so it can run on a Mac or on Windows. And the idea is that you build some code in Q# that controls logic gates. So we're thinking like and or and stuff like that there, but quantum logic gates. So your Q# controller controls the qubits in the computer. And you can write code. There's a full state simulator that supports up to around about 30 qubits. Or you can use what's called the Toffoli simulator, which supports millions of qubits, but is much more restricted in its operation. This is a great resource. There's lots of good tutorials and things to get you started, but it's not the one that I'm going to show you today. If you go to the IBM website, you come across the IBM Quantum experience. And what you get is a composer like this. It only has 4 qubits to work with, but you can actually run your simulation either as a simulation or on an old quantum computer. Basically what IBM are doing is they're working on their 50 qubit machine themselves, but they also have older models that you can run your simulations on in the cloud. So I'll just show you very quickly what way this works. This is a circuit composer, and if you're writing Q#, you also need to know how to work with these are the different logic gates that are available. They're quantum logic gates, and you just drag them down in. So the very first one that I'm going to show you is a NOT. So if you drag an X down and you run your simulation, see this is a NOT gate. It'll take a qubit, which is in a state of 0, and it'll invert it. And what you'll find is that qubit 0 is now 1, but qubit 1 is still 0. So down at the bottom, you'll actually see it reads from right to left. So the first qubit is a 1, so that is this one, and the next qubit is a 0. Right, so that's a NOT gate. This is a C0 gate. So you can put a NOT gate here. So that'll make this a 1. And a C0 is called, it's a control NOT. So what it's doing is it's actually saying, if this is a 1, then invert this qubit. So it's slightly different from normal logic gates. And then at the end, we're measuring the 2 qubits, and we find that they're both 1s. So that makes the top one a 1. And that says, if this one is a 1, then invert qubit 1. Moving on, there is a CC0. So a CC0 is a control NOT. And what it says is if both of these qubits are 1, then it'll invert this qubit. This is really interesting, this one, because this is effectively your universal gate. So if you're used to normal electronics, you know that you can use a NAND or an OR as a universal gate. In other words, you could build up any circuit using just those gates. In quantum computing, it's a CC0 that gives you that ability. So it's an important one to know about. This is also known as the Toffoli gate. And if you think back to the Microsoft, you've got the full state simulator and the Toffoli simulator. Gives you an idea of what sort of operations you can do on it. Right, just 2 to complete this. The first one is this one here, which is an H. An H is a Haramad, which creates a superposition. So if I put a superposition on here and measure that, well then what you're saying is it's in a state of being 1 and 0 at the same time. And when you measure it, you're actually finding, well, I've actually done this with the first 2. So I've got this is a superposition and this is a superposition. And what you find is there's an equal distribution. So a quarter of the time you get 0, 0, 0, 1, 1, 0, and 1, 1. Now, in order to get these figures, we had to run it about 1,000 times. So when you run by default, it'll run for about 1,000 times, and this is showing the averages. So if you run it once, you might find that this is a 1, and that's a 0. And the next time, it could be a 0 and a 0, and so on. But when you build up the pattern, you're actually finding that it's an even distribution. Right, the last one, this is creating a superposition. And what we're actually doing here is we're saying this one will be 1 and 0 at the same time. However, whatever this is a 1, we're going to invert this bit. What we're actually doing here is entangling the 2 bits together. So if you measure any which one of them, what you find is that the other one also collapses to be the same state. So you'll either get a 0, 0 or a 1, 1. Never anything else. Okay? Now that kind of gets you started. Here's some guiding principles. The CC0 is a universal gate. otherwise known as a Toffoli gate. It's common to reverse operations in order to reuse qubits. So in the middle of your calculations, you might do several operations and then undo some of those operations so that you get to, they're a valuable resource and you might have to reuse them. Computations are probabilistic, and therefore you've got to run them thousands of times. So again, back to that idea of it not being instantaneous. The big wins here are because of the way it works in terms of building superpositions. It's not about doing everything in parallel at once. Quantum gates are logical with either a 0 or 1, but can actually yield weird results with superpositions. So what I've shown you has been mostly 1s and 0s. When you start using the different gates where there are superpositions, you're now at the point where you need to understand matrix mathematics. And needless to say, we're going to stop just before we get to that point. Questions, I will be hanging around afterwards if anyone wants to ask me questions about anything you've heard today. This presentation is available online, that's the link, or you'll see it on the video later if you want to. Hope you've enjoyed this talk.